Hello. In the previous lecture, we looked at the three-level laser scheme wherein we had a common ground state and the atoms were pumped to a short-lived state 3 using either a flash lamp uh, or any other pumping process. And the level 3 was very extremely short-lived. Hence, all the population would accumulate in the level 2 and lasing occurred between level 1 and 2. Right? So this was the lasing transition. So we had analyzed this system previously in the context of threshold. So we had made an approximation that at threshold, the photon flux indeed is extremely small, and hence uh, these terms marked in the red were basically ignored. Now what I want to do is I want to look at a more general solution uh, of these governing two equations. These two equations were got in the context of this three-level laser scheme. So let us look at now the steady state in presence of the field itself. That is, we are looking at the steady state of this three-level laser system beyond threshold. To do that, you will clearly see the following. If I take the threshold equations, wherein I replace my P and gamma to 1 in the following manner, that I replace P by P plus sigma times phi. Similarly, I replace gamma by gamma 21 plus sigma of nu times phi. You will see that we will basically get back the same equations. So let me just point that out to you. Remember, it's minus P times N1. Similarly, there is a minus sigma phi times N1, right? So these go together. Similarly, gamma 21 times N2 goes with sigma times phi times N2. Exactly a similar thing happens in the second equation. See that P can be replaced by P plus sigma times phi, and they will go with N1. And similarly, gamma will go as gamma 21 plus sigma times phi. Given this neat observation, I can quickly use this substitution to obtain the steady state solutions of the population inversion. So let me write that out. It becomes N2 bar minus N1 bar. So again, my notation is exactly the same. Here, Ni bar stand for steady state population. So I get here the inversion N2 bar minus N1 bar in this three-level laser model comes out to be P minus gamma to 1. You would recall this factor times N total divided by P plus gamma to 1 plus twice sigma nu times phi nu. Right? Now that you have got inversion, you can ask now what is the gain of the system. Remember, by definition, my gain, the gain would be sigma nu times N2 minus N1, right? And I'm looking at steady state, so N2 bar minus N1 bar. So this leads to sigma nu times P minus gamma to 1 in the numerator, and total. Recall that the minimum pumping was equal to gamma to 1, uh, and that was at threshold. So now we're asking what happens beyond threshold, plus 2 times sigma times phi. So clearly you can see as the field increases, that is as phi, which is the photon flux, increases, the denominator becomes larger and larger, right? And the gain actually decreases. So this is what is clearly seen, where the gain now starts depending on the lasing number of photons within the cavity. Essentially, you know what is happening. There is an equalization of the population, and that is what is leading to this decrease in the gain. So for this three-level system, I can basically, uh, rewrite this in a more suggestive manner, and from where one can actually obtain a very general formula for the gain, which is not necessarily limited only to the three-level laser model that we have. It is a more general expression that governs basically gain saturation. So let me come to that. Uh, so for the three-level laser model, I can rewrite this equation in the following form. I can take sigma nu, these prefactors out, take the pumping and the gamma 21 from the denominator, and this becomes like a prefactor, and this I can multiply by to 1 by 1 plus twice sigma. Remember, it's a function of nu. You're looking at photon flux at nu, and divide this by p plus gamma to 1, right? So you see, I can rewrite my gain in the following form. And the form is extremely general. I can rewrite this as g naught of nu, right? This is my prefactor, and this is 1 plus phi nu divided by phi nu saturation. So here I'll quickly identify these two terms, right? I've used the definition that my G naught of nu is simply this prefactor which I had written down here. That is sigma nu P minus gamma 21 times N total divided by P plus gamma 21. And the phi nu saturation, which is another parameter, is simply this other denominator, which is P plus gamma 21 divided by twice sigma nu. Now, this is a very interesting and a very general form for the gain. The G naught of nu is known as the small signal gain, right? This quantity is known as a small signal gain. It is obvious why. That is, if I set my photon flux, that is the lasing number of photons within the cavity, to 0, then this is the gain I would get, right? That's why it's called the small signal gain. And it's important to note that the largest gain possible in the system is when this term phi of nu is actually 0, right? If you look at this term phi of nu is what is decreasing the gain. If I set this to 0, what I get is basically the largest possible gain, which is the small signal gain. So there is a scale to the number of photons with the cavity that leads to a decrease in the gain. And that scale is set by this term, the phi saturation. So when phi equal to phi saturation, clearly you see that the gain decreases by a factor of half. So you see that the total gain becomes half of the small signal gain at phi equal to phi saturation. So these are two very important quantities that one needs to keep in mind. And this form of the gain, I would like you to remember, and this is a very general, generic form for the gain, uh, which basically tells you that it is the largest gain is a small signal gain divided by 1 by 1 plus intensity of the lasing photons divided by the saturation intensity. We can clearly arrive at the formula for I saturation. So I nu saturation can be written down in a similar fashion. You simply multiply by H times nu P plus gamma 21. Remember that h nu times phi, the photon flux gives us the intensity. Hence, we can write this. I'm essentially repeating myself. This form of the gain coefficient is very generic in the sense that as the intensity of the lasing photon tends to zero, you see that the gain becomes maximum, it goes to the small signal gain. This feature and this kind of power law dependence on the intensity is a generic feature of lasers. Usually, both of these parameters, that is the small signal gain as well as the saturation intensity, these are experimentally measured parameters. Only in this case of the three-level model, we are actually able to obtain these following forms for these two parameters. The generic dependencies are very clear in the sense that, for example, the small signal gain is proportional uh, to the scattering coefficient. Larger the scattering coefficient, greater is going to be your small signal gain. Similarly, larger the scattering coefficient, there is a strong coupling between the atom and the light, and hence it lowers the level at which saturation happens. One important thing to realize, which I did not mention, is that the phi saturation, the amount of intensity saturation or the photon flux saturation value depends on the amount of decay in the system. And larger the decay, larger is going to be the flux of photons required for obtaining saturation. So these kind of dependencies are absolutely generic, but the actual form for this has been obtained only for the three-level system, even though this final form of the gain is quite general and applicable very widely. So now let's look at homogeneous broadening so that we also put in this frequency dependence into this gain formula. So if you recall, let me just quickly write down a formula which we have of course seen earlier. For example, my sigma of nu e square by 4 pi. I'm looking at the classical that we got earlier, right? Times delta nu to 1, which was the line width of the Lorentzian, and had nu minus nu to 1 whole square plus the delta nu to 1 whole square. I can as well write it down in a more succinct manner as sigma nu to 1. That is, I've taken this at nu equal to nu to 1. So I get this prefactor divided by 1 by delta nu to 1 as there, and then one can write down this form as 1 plus nu minus nu to 1 whole square divided by delta nu to 1 whole square. Right? This is the form for the scattering coefficient. Let us put this form back into my g of nu, which is my gain coefficient, and this is simply g naught of nu 1 plus, either I can use the intensity or the photon flux. There is hardly any difference there. And you see, if I now put in the explicit forms and I can rewrite this, I'll just indicate a little bit of algebra and you can easily follow that up. So my g of nu was sigma nu. This is particularly true for the three-level laser model that we have. P minus gamma to 1 times n total, right? This was the g naught of nu, P plus gamma to 1 times 1 plus phi by phi saturation. What I'm doing is basically multiplying and dividing this by the following, that is sigma nu to 1 divided by sigma of nu. Similarly here, sigma nu to 1 divided by sigma nu. And you see now I can cancel a few terms, right? And I can rewrite this whole thing in the following form. which is G naught of nu to 1. Remember, this will contribute to that, divided by 1 plus phi by phi saturation times the sigma nu to 1 by sigma, which simply happens to be uh, that factor, which is 1 plus nu minus nu to 1 whole square by delta nu to 1 whole square. Now quickly remember that phi nu to 1 phi nu saturation or phi nu to 1 saturation can be written down as P plus gamma to 1 divided by twice sigma, but now at sigma at nu to 1, that's at the line center. So given this, I can, you see this product will take care of that. And expand this denominator and carefully cancel out the terms which are related to this ratio of sigma nu to 1 by sigma. And what we get is the following, that G naught of nu to 1, which is the gain at the line center, divided by 1 plus nu minus nu to 1 whole square divided by delta nu to 1 square plus phi by, now phi saturation, but this is at nu to 1, right? This is the line center saturation. We are distinguishing between phi saturation and phi saturation at nu to 1. So this is the final form you get. What are the consequences of such a relationship for the gain? So let's look at it pictorially. I'm plotting now g of nu divided by g naught of nu, right? Gain divided by the small signal gain. And my vertical scale is going from 0 to 1 clearly, and my horizontal scale is in terms of the detuning, which is scaled detuning, that is nu to 1 minus nu, right, divided by delta nu to 1, right? This is a scaled detuning. So at nu equal to nu to 1, I'll be sitting here at 0 at the line center, and then that's so what you get is basically the Lorentzian forms. And this, for example, is the situation when phi by phi saturation at nu to 1, when this quantity is very small, right? And you will see that when this quantity, so this is, let's say, the level of 0.5, and this corresponds to this fraction being equal to 1, right? So you see, as we increase the photon flux within the cavity, the gain actually saturates, and this is what is called as gain saturation, right? This is even for a higher value of the photon flux. For example, here the fraction could be as large as 5, right? So as you increase the light intensity within the cavity, you see that the gain coefficient is coming down. Similarly, one can, for example, plot, if you like, I'll encourage you to plot the second dependence as well, which is look at it as a function of the photon flux itself. So I'm plotting phi nu by phi saturation, right? Um, Nu to 1. And again, uh, I'm plotting this ratio of the gains, right? So I'm plotting g of nu by g naught of nu to 1. Imagine you are on resonance, then you see that your because of uh, saturation of the gain will fall from 1 to a lower value. This is, I'm looking at on resonance, that is nu minus nu to 1, divided by delta nu to 1. This parameter is 0, this on resonance. So let us say that is, you're sitting at this line center and you're asking, as you increase the photon flux, what happens? So you're tracking the peak of this curve and the peak falls off. Similarly, if you look at now, let's say you started at a at a detuned position. For example, nu minus nu to 1 is plus minus 1. For example, you can start from 0.5 and you would decrease. Similarly, you would decrease as you go away in resonance, you will go even lower. So you see that this would be for various values of this parameter. For example, this was plus minus 1. You would get, of course, is symmetric. This could be for the situation when you're plus minus 2, right? You're essentially a delta nu to 1 away, which is the width of the Lorentzian. As you go away uh, and as you increase the photon flux, you see that you actually decrease the gain at every frequency. This is indeed true for, homogeneously broadened laser transition, which has this Lorentzian line shape. So my delta nu gain, right, the width of the Lorentzian is basically delta nu to 1, which is determined by the scattering coefficient or absorption coefficient, but it has got this photon flux dependence or intensity dependence, if you like, right? Depends on the lasing number of photons within the cavity, and it is scaled with respect to a saturation value at which the gain becomes half of the small signal gain, and this now is my new width of the gain coefficient. Clearly see this is what we discussed even earlier as a power broadening. The response not only decreases, it also widens in terms of frequency content. So this phenomena of the gain saturation is also known as bleaching. So we have looked at this very two important characteristics of the gain, which is the notion of a small signal gain and also gain saturation. What is the consequence of saturation to the spatial distribution of gain within the cavity? So that is something that we'll explore in the next lecture.